it's really nice to be back here in Elixir Conference, United States. Last time that I was here in person was 4 years ago, and it's very interesting, like, to see how many things happened in the Elixir community in those 4 years, right? Like 4 years ago, nobody was talking about Elixir and machine learning. Now there are companies deploying machine learning features to their products with Elixir. 4 years ago, Livebook did not exist, and today it has become a great tool to onboard new developers into the ecosystem. 4 years ago, Erlang was not JITted, and then I think it was 2 years ago when they launched the JIT, and it made pretty much everything at least 33, 50% faster, but some people saw speed ups of twice, 3 times faster. And perhaps the important part for this talk is that 4 years ago, we are not talking about Elixir potentially having a type system. So, and that's going to be my focus for today. I'm going to ask a little bit of your patience. I'm going to take the full hour that was allotted to me, perhaps a little bit more, but I hope it's going to be worth it. So what are the goals for today? So I want to align expectations, first of all, because when I say a type system, it's likely that everybody here has something different in mind, right? Like based on the other languages that you used, the company that you worked at, the team, the industry. Who used a typed language before, right? Can you shout me some names? Type language that you use. TypeScript, I guess, is going to be common. What else? Haskell? C#? C++? OCaml, F#, Java. Cool, right? So that's my point. We have to align expectations. Everybody kind of has a different background. I also want to address concerns and doubts. In preparation for this talk, I had people send questions on Twitter. I had people lay down their concerns on Elixir Forum. I asked them to. And I want to talk about this because my general impression is that the community is enthusiastic, positive about those changes. So it can be easy for people who has concerns and questions about those changes to have their voices drowned out, and we need to make sure that everybody's heard. And we are going to do this, all of this, by talking about gradual set theoretic types, which perhaps it doesn't mean anything to you right now, but at the end of the talk is going to be very clear what it is. So before we go into the bulk of the talk, I want to do a quick recap of what has happened, what has been announced. So we announced last year that there is a PhD scholarship to research and develop a gradual type system for Elixir. Guillaume Duboc is a PhD student. Professor Giuseppe Castagna, which I'll most likely refer throughout the talk as Beppe. He is the senior researcher. He has been working and researching type systems and set theoretic types for decades, and I'm also involved in the project. And this is, for me, this is a classical research and development project. So we started with the research stage. And what we did when we were researching is, well, Elixir is an existing programming language. When you're starting a programming language from scratch with the type system, then you can change the language to accommodate the type system and vice versa. But Elixir is an existing programming language. We don't want to change. We don't want to break the code. So what we have to do is that if we want to add types to Elixir, we need to get a type system. In this case, we're getting one based on set theoretic types. And we have to get all the features that exist in Elixir, right? Like the data types, the syntactical constructs. We have to get all of them and model them in the type system, right? And when we do this, if there's not a lot of good fit, if you're like, oh, we only covered 40% of Elixir features, then that would mean that that type system that we picked would not be a good choice for Elixir. So what we do is that we start mapping all Elixir features, all Elixir semantics to set theoretic types. And there is no type system today that is going to cover everything that we have in Elixir. So we are going to find areas of incompatibility. And what we did is that we developed new theory to cover the areas, the features in Elixir that the type system could not cover. And by we is Beppe and Guillaume. So we augmented the theory whenever necessary, and then we wanted to publish the results and collect feedback. And we have done all those steps so far, right? So 2 months ago, I did a blog post saying, type system update, saying that the project has effectively moved on from research into development. We'll start now implementing the model and the type system that we have defined. And we published the paper. You can access the preprint. It's going to appear in an academic conference really soon. And if you go to the Elixir website, if you get that blog post, it's going to have a link to the paper. So if you are like let's say a type-curious person, you like to know how type systems work, you can check out the paper. The paper, we try to make it very accessible, but it's still more on the academic side. Okay, so at this point, before we continue moving forward, I think it's important to do 2 disclaimers, okay? Even though we are very happy with the results so far, we may not have static typing after all, right? We are happy with the research, but we still have to implement it, and there are still a lot of things that can go wrong. So it can be that, in 1 year, 2 years, you're like, well, we tried, but it didn't work for reasons X, Y, and Z. And the other thing is that this talk, and in particular the paper, they are in-depth explorations. Like, if we add a type system in Elixir, if we are successful, you don't have to read the paper to use the type system, right? You don't have to grasp everything that I'm going to talk about today to use the type system. It's like using a programming language, right? Like, we can all use a programming language, but if we want to implement a programming language or understand how things work internally, then we need to develop a different set of skills. So here, going more in depth to set up the foundation so we can discuss why we have made certain decisions, certain trade-offs, and so on. And this is all possible because it's a partnership between the CNRS, which is the biggest science research institution in Europe and remote. And the development is being sponsored by Fresha, Starfish, and Dashbit. So if you are looking for Elixir opportunities, don't forget to reach out to those companies. All right, that's the recap of what has been announced at the very broad sense. So now I'm going to go into the deep end of the talk. We're going to start talking about types, why we want types, how it works, and so on. So last year, I gave a talk at ElixirConf Europe that was talking why static types? Why would we want to have static typing in Elixir? And I'm going to briefly recap this talk today, because my goal for this presentation is to cover kind of everything that I know about the type system work so far. So we kind of have a unique reference point that we can share with the community. So I'm going to briefly recap the talk. And why static typing? And in the talk, I've mentioned like 5 main points. I talk about code maintenance, performance, documentation developer experience, using types, static typing as a design tool, and using static types as proofs. And most of the talk, I was actually talking about code maintenance. Because when you're going to have, when you join like a discussion about typing online or offline, sometimes things tend to get heated. Sometimes you start to hear claims that you think, it's like, I don't think this is true or like generally applicable. So a lot of the discussions when people are talking about types, they tend to focus on the code maintenance aspects. And I think we should look at it with care, because what can happen is that if we add a type system to Elixir, and I'm going to show some examples, if we add a type system to Elixir, and then everybody thinks like, oh no, because I have types, my code now is bug-free, and I don't need tests nor documentation, we are going to end up with actually worse code at the end of the day, right? So, for example, some of the claims that I hear is like, hey, if you have types, you can write fewer tests. And honestly, I can't see like this being true. Like maybe if you have types, you can write fewer bad tests, right? But not generally. And then I can come up with like dozens of examples. So for example, let's take this average function. And here is the I'm using the proposed type notation that we are using for Elixir type. So we'll use the $sign. The joke is because that when we add types, that's how we're going to make money. So we do the $sign, and we're like, look, the average function is going to receive a list of numbers, is going to compute the average, so it returns a number, right? And according to the types, this is a perfectly valid implementation of this function, right? Like the type's like, yeah, it gets a list, returns a list of numbers, returns a number. This is good, right? But that's not how average behaves, right? It is for a list with one element, but other than that. So another example, like same idea. Imagine that we want to implement something very simple, a Boolean operator, and if it receives 2 Booleans as arguments, return a Boolean. Also a perfectly valid implementation. Right? It's meant to be, if you receive true and true, it returns true, otherwise it's false. But this is perfectly valid according to the types. So I don't think that, generally speaking, it will say like, hey, if I have types, I can write fewer tests. And I want to be very emphatic about this because, again, if that's how we approach this problem, it can be that at the end, we are going to have worse software. Right? So it's very important for us to understand like what we are getting. Something else that I hear is that types leads to significantly lower bugs, right? I've heard people saying like a type system would have caught like 80% of my bugs, citation needed, right? And maybe it's true for certain environments, certain industries, certain programming languages. But how applicable it is to us in the Elixir community. So for example, just to provide a counter argument to this claim, there is a paper from, I think it was from last year or 2 years ago, Types for Code Maintenance, to type or not to type, a systematic comparison of the software quality of JavaScript and TypeScript applications on GitHub. And you can check out the paper, and looking at TypeScript is useful because it's a dynamic language that got a type system. As we're going to see, our type system makes like very different trade-offs to the TypeScript one, but in any way, it can be a useful reference to us, right? And then in this paper, we have things like the analysis indicates that TypeScript apps exhibit significantly better code quality and understandability than JS apps. This is good, right? Like, if we can get this, I'll take it. Contrary to expectations, however, bug proneness and bug resolution time of our TypeScript sample were not significantly lower than for JavaScript. Our results indicated the perceived positive influence of TypeScript for avoiding bugs in comparison to JavaScript may be more complicated than assumed. While using TypeScript seems to have benefits, it does not automatically lead to less and easier to fix bugs. And you can read the paper, right? And this is just an example. You'll be able to find papers where claims the opposite. It's like, yeah, no, for this study, a type system led to fewer bugs, right? And then we can go and talk about this, talk about those papers. But to me, at the end of the day, I don't think that's a very useful discussion. Because we are saying, hey, it leads to significantly lower bugs. But like, which kind of bugs, right, is it helping us catch? So for example, the Rust type system, the Rust compiler and the type system, it actually guarantees that you're not going to have certain bugs in your software, that you're not going to deallocate memory twice, right? So it will effectively lead to fewer bugs. You're not going to deallocate memory twice. You're not going to use deallocated memory, no data races in threads, dangling pointers. But we don't have any of those problems in Elixir, right? So getting the Rust type system and applying to Elixir would not necessarily be useful. So saying types leads to significantly lower bugs, for me, like, this is too simplistic. That's not the discussion I want to have, right? The discussion I want to have is, well, which bugs can a type system actually catch? Or if we're going to add a type system to Elixir, which bugs it will catch? And for us, I think the thing that we're interested about is this. Imagine that we have this code. So some function receives an argument. This argument calls another function somewhere. It could be another function in Elixir, in a library, or even on your own application. You call another function. And what we know from this other function, this another function, is that it returns a string. So what we do is that we pipe the result, we pipe that string into a string.split, and we split that string. However, code changes, right? So it can be that in the future, this another function now starts returning a string or atom, right? And then if we have a type system, what a type system would do here is to say, hey, actually, you may have a bug here, because there's this another function that now can return an atom. And if you pass an atom to a string split, it's going to crash. So the type system can no longer prove, okay, that this code is going to be correct under all circumstances. It may actually be so that for all the arguments that we call some function, the atom is never returned, right? So it may be that the bug does not ever manifest. But the point is that the type system can no longer prove, it cannot prove that it's going to work under all scenarios according to the types. And that's what I like to think about. When I think about types, I want to think about types as proofs. Like the types help us prove certain properties about our code. And then if we understand that, if we understand the guarantees that a type system can give us, right, then we can use that in our favor in order to write better software. So to sum up, right, code maintenance, I think the hope is that, yes, it's going to improve code maintenance. But as I said, this is such a topic with, let's say, so many claims that I'll say, OK, I don't like to think much about this aspect. I like to think about types as proof. So I said, OK, code maintenance is going to be in yellow. It's not something that we're necessarily going to get in Elixir. I don't like to think about significantly lower bugs, not helpful. Performance. The focus for the type system, maybe in the future, we can use it to improve performance, but that's not a concern that I have right now as well. And we are going to see throughout the presentation why I'm not worried about this. But with static types, we are going to get better documentation, because that's pretty much how we use type specs today for documentation. But we can also get better developer experience, right? Because if we look at the code here from this previous slide, if we have good error messages and quick feedback that something may be wrong here, that's excellent. That's fantastic. So it can improve documentation, developer experience. We can also use types as a design tool. There are people, when they have a problem, the first thing that they do to start addressing the problem is to write the types for that problem, right? And me personally, sometimes when I have a problem, I start with the documentation. Sometimes I start writing the tests. Sometimes I start with the code, because if I'm not sure I have to do a prototype, I start with the code. And it can be another tool for us. Like, hey, I'm going to start solving this problem by writing the types first, which is something that we can do. And we also want to use static typing as proofs. So that's why static typing in Elixir. So far so good? All right, so now let's talk about set theoretic types. So if those are the benefits that we are expecting to get, how we are going to get them? And the goal is that we're going to get them through set theoretic types. And set theoretic types sounds like a very fancy word, but what it means at the end is that it is a type system based on unions, intersections, and negations of sets. So to me, this is very exciting, because if we can have a type system where we can reason using the set operations, oh, I have two sets. What is the union of those sets? What are the intersection, right? Which is something that we learn in middle school or high school. Then it can be a type system that is potentially very easy for us to reason about. It's going to be very accessible. So to me, this sounds very exciting if we can have type system based on those operations, those fundamental operations. And the way it looks is that, yeah, we can think about sets. So for example, if we have the type atom, you can think this is a set, potentially an infinite set, because we have infinite atoms, right? And then OK, the atom OK is going to be part of that set, right? It's going to be part of that type. The atom error is going to be in that type as well. And it's even interesting because we want OK to be a type as well, because we want to say, hey, this function returns the atom OK. So we say that OK and error, those are also singleton types. Those are types where they only have one, that they represent themselves. Like if you think that atom is infinite, right, have infinite entries, the type for OK only represents a single entry, so we say this is a singleton type, right? And then, yeah, we define a set for all the atoms. We define a set for all the integers. We define a set for all the floats, right? So we define a bunch of sets. And you're like, OK, in Elixir, we have this thing called number. So we have like the isNumber guard, which returns true if it receives an integer or a float. So with set theoretic types, we would just say, hey, number equals and integer or float. So in the type system syntax that we are using so far, we are using OR to mean union. And we also have intersection. So we could say integer and, so and is the intersection, and float. What is the result of integer, intersection, float? We can see they don't have anything in common, right? So this is going to be the empty set, which we call none. So we are only thinking about sets, right? And we start to apply this to everything. So the byte size function is a function that receives a binary and returns the number of bytes in that binary. So we can say that this function is going to have the type binary, arrow, integer. We also say binary to integer. And we say arrow types often for functions exactly because it has that arrow there, right? So a byte-sized function receives a binary, returns an integer, right? And then we can get like the remainder operator as well. And it's going to say, hey, you know, the remainder operator receives 2 integers and returns an integer. And that's the type for it. So the functions, they also have types. And we have a set that represents the types of all functions, right? And that's the function set, and so on, so on. OK? So far, it has been, OK, we are thinking about sets. But our sets, they have been quite disjoint so far, right? Like atoms don't have anything in common with functions, right? Functions don't have anything in common with floats, right? They're all disjoint. The intersection between them is empty, as we saw between integer and float. So let's see some more complex examples, OK? So imagine that we have this function, int negate. All right? It's a function that receives an integer, returns an integer. So int negate receives an integer, check that the argument is indeed an integer. And wait, there's a typo. It's meant to be int instead of num, OK? So it negates the int, right? So it receives an int and negates the int. A regular Elixir code with a type signature, with the new type signature on top. And then imagine that we also have a bool negate, right? That receives a boolean, right? And then negates that boolean. So this function receives a boolean, returns a boolean. So we know that in Elixir, we can kind of merge these 2 functions into one, right? We can make that those functions become clauses of the same function. Apparently, I made a typo on all slides. Yeah. But anyway, right? So now we have 2 clauses, right? Negate when it's integer, negates the integer, negate for a boolean, negates the boolean. So here's the question. Now that we merge those clauses, let me roll back here just so we compare, right? So here's how it was before, right? Like we have 2 separate functions with their types, and now we merge them as different clauses of the same function. What is going to be the type of this function, right? So we can think it's like, hey, it's going to be something like integer to integer, something that we don't know what it is, union or intersection, boolean to boolean, right? So we can say, hey, this function has a type integer to integer, or, which is the union, boolean to boolean, or we can say integer to integer, and, which is the intersection, boolean to boolean. So I'm going to ask for a show of hands. What do you think it is? And when I was asked this question, I got it wrong, so don't be shy. The goal is that even if we get it wrong, we are going to be able to reason about this, right, and understand it using set theory, OK? So who thinks it needs to be a union? Please raise your hands. OK? Who thinks it has to be an intersection? We want to say integer, integer, intersection, boolean, boolean. Okay. So, sorry? No, there is no catch here. There is a catch, but not that catch. So, let's think about this, right? So when we have a set, atom or integer, the atom OK belongs to the set, right? Because, hey, OK, it's an atom. So as long as we satisfy any of the sides of the union, right, it's fine. The number 1, 2, 3, 4, right, it belongs to the set because it's an integer. So as long as we satisfy any side of the union, it's part of that set, right? That's how set theory works. So imagine that we say that our answer is integer to integer or union Boolean to Boolean. This is a valid answer. This is a valid type for this code. However, it has a problem. This type is not very helpful. This type is too generic because, as we just showed with atoms and integers, right? This type here, integer to integer or Boolean to Boolean, is also a valid type for this code, right? Because as long as I satisfy one of the sides of the unions, we are going to be happy. It's like if I say, look, this t-shirt here is gray or blue or red. The fact that I say or blue or red did not make it false. It's still gray, right? But it made it less precise. I'm adding irrelevant information. So integer to integer or Boolean to Boolean is also a valid type for this because we satisfy the integer to integer part. The or Boolean to Boolean is just not useful, right? And it's also going to be a valid type for only the other part of the function. Okay? So the issue with using the union here is that it's just too generic. It's not actually capturing the intent of the code, right? Because if it's a valid type for only, if you can use the same type for only half of the code, then it's not really capturing what the code is doing, right? Really what we want to think about, right, is that, hey, here what we do is that we have a function that can do integer to integer and Boolean to Boolean, right? It can do both of those at the same time, which is the intersection, right? So that's the idea, right? So that's why we do integer to integer and Boolean to Boolean. It's the intersection. It can do both, right? So now when we're talking about set theoretic types, there's this important concept that we say that is type precision. We want to provide the most precise type possible for a function, because if the type is precise, it's going to more closely capture what that function does, right? And we can reason about this precision like intuitively in this example. Imagine that you have two sets, okay? A and B, like we have integer to integer and Boolean to Boolean. If those sets are different from each other, the intersection between them, right, like the part in the middle, right, is always going to be smaller than the union of the sets, right? So that's the idea. We want our types to be precise so they can capture what the function does. So let's continue thinking more about this, more examples, right? So if we had this code today, and we were to write a type spec, the ones that we have today in Elixir, for this code, we would most likely write this, right? We would say, hey, there is a negate function that receives an integer or Boolean and returns a integer or Boolean, right? Which, if we were to write to the new type syntax that we are exploring, we would get this. This function is integer or Boolean to integer or Boolean. Is this type more precise or less precise than less, right? Because the other types, this one is saying, hey, if you give me an integer, I can return an integer or Boolean, which we look at the code, right? That's not possible. We look like, hey, you know, like if you give an integer, it always returns an integer. But the type saying, if you give me an integer, I can return an integer or a Boolean. Again, it doesn't make the type invalid because it's about the t-shirt, right? I can say this is gray or blue or green, right? The fact that I added or blue or green did not, it's still valid, it's still gray, right? It just made things less precise. You're adding not useful information. People on the left as well can see it's gray. All right, so if you're thinking about type precision, right? So this integer or Boolean arrow, integer, or Boolean, it's not very precise, right? And then integer to integer or Boolean to Boolean, okay, is kind of in the middle, let's say, and then we have integer to integer and Boolean to Boolean being more precise. So you can say like, José, this is cool, but that seems to be like a very easy typo to make, right? Like you type or instead of and, like the examples, the two examples here in the middle, or, sorry, in the middle and at the end, and it can be an easy mistake to make. Right? So we are doing a couple things to make sure that we're not making mistakes and that we are providing precise types whenever we can. So the first one is that the type here in the middle, it just has no use in Elixir. There is no situation where this would be useful. So if you write that, so imagine that we add a type system to Elixir and say, hey, I'm doing the union between the arrows, right? Integer to integer or Boolean to Boolean. We're just going to say, hey, unions between functions of the same array, they have no use in Elixir. We'll warn and say, you wanted to use and instead. Right? And then maybe we'll talk a little bit about type precision and so on. The other thing is that we'll also allow you to specify intersections between arrows, right? The arrow is, again, integer to integer, Boolean to Boolean, as multiple signatures to mirror the Elixir code. So we are going to allow this type to also be written as this. And you can have them close to the clauses if you want, but this is going to be closer to the Elixir code, right? And it's going to push us to write, and this is the same as intersection. It's going to push us to write proper types. All right, good? So we are talking about set theory, unions, intersections. We didn't talk about negation yet, right? But we are talking about set theory. And then we're talking about type precision, right? Like, oh, there's idea of like, we want to provide the most precise type as possible. But you may ask, why? Right? Like, sure, you have to provide the most precise type as possible, but why, right? Please explain why. I haven't told why yet. So let's see why with an example. So imagine that we start with this code. So again, I have a subtract function here, and it receives 2 arguments, 2 integers. It returns an integer. The implementation of subtract is going to be A plus negate B, right? We are going to negate the second argument. And the implementation of negation is a function that receives integer to integer. Okay? Oh, this one is correct. Yes. So the negate function here receives an integer and negates that integer, right? So we've seen the negate function before. So imagine that we wrote this code. Elixir has a type system. We wrote this code. We added those types, right? And then somebody in the future comes and add another clause to negate, the clause for Boolean, right? And then when it receives a Boolean, it negates the Boolean. What is the type of this new function? If we use the type that we know, like the least precise type that we've seen, right? If we use this type, what is the issue with this? If we use this type, the type system will actually complain because this type is saying, hey, when we call negate, passing an integer, negate's going to return integer or Boolean. Then the type system is going to look at this and say, look, you are trying to add an integer, which is A, with a Boolean, which is the result of negate, and this is not valid. Right? So because the type is saying, look, this function returns integer or Boolean, we gave like the not very precise type, the type system is going to think, hey, I can no longer prove this code is correct, so I'm going to error, I'm going to raise a warning, and they're going to look at this, they're going to be unhappy, because they're going to look at the code and say, hey, like the type system is complaining here that is going to add integer to Boolean, but the code, that could never happen. And that's all happening because we did not give it a precise type, right? Because the type checking is going to work based on the types that we provide, okay? However, if we use the precise type, which we know we can write it like this, when we call negate with an integer, right, it says it's going to return an integer, and then the type system is going to say, hey, you want to add A, which is an integer, to the result of negate with an integer, which is also an integer, and everybody's happy, everything works, right? So type precision is important because the more precise the types, the more precise the type system is, right? So if we provide precise types, we're not going to have false positives. And that's why the whole idea behind, that's why it's important for us to have unions and intersections, right? Because if all we had is unions, like the dialyzer example, the type spec example that we wrote, our types would not be precise, right? Our types, they would not be expressive enough. And now when we started typing Elixir, we would get a bunch of like false positives, like this code. We would get code that says, hey, you know, there is a potential typing error here, but this typing error is not possible to happen, all right? So that's it. The more precise the types, the more precise the type system, right? That's why we want type precision. So we get precise warnings, precise errors. If something happens, if something is wrong, we want to be sure that that thing is indeed wrong. It's not a false positive. And in order to do that, we need an expressive type system where we can do unions, intersections, something that can capture the intent of the code as close as possible, okay? So that's why set-theoretic types. They express many of Elixir idioms with precision, and they provide a foundation for reasoning. When we have to reason, hey, we are thinking about unions, we are thinking about intersections, okay? So that's what attracted me to set-theoretic types, and that's why we have been quite successful so far to capture Elixir code, Elixir idioms in set-theoretic types because, yeah, it's quite expressive and allows us to capture all the intent of our Elixir code. However, set-theoretic types is just half of the equation, okay? Because here's the thing. Elixir exists today, right? We all have written a bunch of Elixir code, right, that already exists. And we don't want to say, hey, Elixir 2 is typed. None of the code you wrote before works anymore. You have to write type definitions for everything, right? Because everything that we did so far, all the examples that I've shown so far, it's assuming that we are explicitly adding the type signature to all functions, right? But there's existing Elixir code today. And we want to make sure that when we add a type system to Elixir, all the code that we have written today is taken into consideration. And we do that, one of the disciplines that allow us to do that is called gradual typing. Gradual typing introduces a new type, right, a new set for us, right, which is the dynamic type. And the idea of the dynamic type is that the dynamic type is known at runtime. Like, we really don't know it at compilation time when the type checker is running what dynamic is. So when you have dynamic, it means that we can't prove much about it. If our code is full of dynamic, the type system is going to be like, hey, I actually can't prove much. I cannot try to find a lot of the bugs, right? It's quite limited what the type system can do. If no type is declared, it is assumed to be dynamic, right? And it leads to this joke, right? Somebody can say, hey, Elixir is typed today. It just happens that all the code receives dynamic, right, and returns dynamic, because that's how our code works today, right? So when we add gradual typing, we're going to start with the idea that if you don't add a type signature, okay, the arguments are going to be dynamic, right? Which means we don't know what they are. We only know at runtime. We can't check anything at compile time. A lot of people say that gradual typing is the best of both worlds. Is this true? Well, if the dynamic type is not used, then it behaves as a static type system. So if you have a gradual gradual typing, and then in your code there is no dynamic, it behaves the same as a static type system. This is important. It's not because it becomes gradual that the whole thing becomes less useful. No, we can only prove less when the dynamic type is involved. On the other hand, the more the dynamic type is used, the fewer guarantees you get, okay? So let's see some examples. Let's see some code. So imagine we have this code. The identity function, right, receives an argument, returns an argument, and we have the debug function that receives an argument, calls the identity function, okay? It's a simple code that's going to reveal so many problems. So we call the debug function that calls the identity function, and we concatenate those strings, right? Concatenate those binaries. So if I call debug foo, it returns we got foo. Now imagine that we wrote this code, and then we add types to Elixir, Okay, we add types to Elixir, and somebody who implemented the identity function, they're like, oh, actually, when I implemented this function, in my use case, I expect the argument to always be an integer, so I'm going to add the type integer to integer. But no types are added to debug, right? So now we are in this boundary where we have dynamic code, which is debug, right? And debug has to call statically typed code. Right? And we're going to see there's going to be a lot of friction in this, okay? Because here's the thing, right? So, all right, so we add a type to the identity function. We say, look, this thing is actually meant to receive an integer, return an integer. Then debug calls the identity function that is, right? And all the code is the same. And imagine that now the type system has to type check the debug function. As we said, if there are no arguments, if we don't declare the type signature for the debug function, the argument is going to have the type dynamic, right? So what we know here is that arg has the type dynamic, right? So when we call identity function with the type dynamic, what is it going to return? The simplest answer is to say, look, if we call identity with the type dynamic, we can't say much about it, so we're just going to say that it returns dynamic, right? But this, if you look at this code, right, like it's very weird because, you know, we know that the identity function says that it returns an integer, right? It says it returns an integer. So what we are trying to do in the debug function is to concatenate a string we got with an integer, which is not valid. So according to the types, this should crash. But if we say that when something is called with dynamic returns dynamic, there is no crash. So can you see, like, when we're trying to interact the dynamic part with the static part, like, things start to get, like, really weird. So according to the types, we are supposed to get a typing bug. We're supposed to get a compilation error, but we don't get any error. We don't get any warning. And somebody can say, hey, like, this is pretty weird, right? So when we're talking about this intersection between static and dynamic, one of the ways that we can solve this problem is exactly what we did. We're going to say, look, if you call something with dynamic, it returns dynamic, but then the dynamic starts to spread everywhere, and then you have bugs like the one we saw, right, where the identity function says it returns an integer, and we apparently are fine with concatenating an integer with a string, right? So it feels weird, right? So you can say, okay, what if, so let's try something different. That looks weird. Let's try something else and hope it's less weird. So imagine that we have, again, same example. We have the identity function, receives an integer, returns an integer. And then we have the debug function. We know because debug has no types, arg is going to be dynamic. Now imagine that we do this. Just, okay, if I call identity with dynamic, which is something that we don't know, you know what? I'm just going to ignore the dynamic. If I call identity with dynamic, identity told me that it returns an integer. The developer wrote that type, so let's trust the developer. What could go wrong, right? So we say, look, identity, if identity is called with dynamic, right, it's going to return an integer. So if identity call with dynamic returns an integer, we are going to say, hey, I'm trying to concatenate, string concatenate something with an integer, and we get a type error. And you're like, yes, victory, right? Like, this looks pretty good, right? So we got a compilation error, which is what we wanted. The type system was able to find the bug. And then somebody goes to the code compiles just fine because the type checking for the dynamic part is optional. And then somebody goes to the terminal and calls debug foo, and the code still works, right? So like, wait, how? Like, the compiler told me there is a type error in that code, right? And it still works, right? Like, when I called it, everything was fine, right? Not only that, right? If we go and try to debug that code, if we put like a dbg on the identity call, it says it's going to print a string. And then you're like, how can this be? Identity is telling me that it returns an integer, right? But when I debug the code at runtime, I can see a string, right? This is equally confusing, right? It's just a different type of confusing. So what we can say, well, in the intersection between static and dynamic, another option to solve this problem is to ignore dynamic, right? So if we call a function with dynamic, we say we're going to trust the types the developer wrote, and we're going to maintain its return type. This is similar to what TypeScript does. And we say that this is not sound. And the reason why this is not sound is exactly because the type system says, hey, this thing is going to be an integer, but when we are debugging the code, we can see a string, right? So the types at compile time, at runtime, they do not match, right? But anyway, that's another option. That's something else that we could do. So at this point, you're like, all right. Like, we had those two options. We can try to go the runtime way and just ignore the static checks. We can try to get the static typing checks, but the code is the types are going to mismatch at runtime. What other options do we have? There is another option, which is, well, again, same code. When we call identity with dynamic, if we call identity with dynamic, identity says that it returns an integer, right? So we're going to say, look, identity, if you tell me that you return an integer, I'm going to accept that, but I'm not going to trust you. I'm going to add a runtime check to guarantee that when I call something with dynamic, like the boundary between dynamic and static, right, I'm going to add a check to guarantee that it will indeed return an integer. And then when I call it with debug foo, right, we get a type error. So now we're happy, right, because the type system told me there is going to be an error. When I call it, I get a type error. So we're able to make everything consistent, because the other options are not consistent, right? Now we're able to make everything consistent. But what is the problem with this? So option 3, introduce runtime checks. If we call a function with dynamic, we keep and check its return type, right? The problem is that it introduces performance costs. Every time we call static code from dynamic code, we need to introduce those checks. As the data structures, they start to become more complex, they start to work with collections. You are adding more and more checks, and everything becomes expensive. So at this point, you're probably, right? It's like, we have to solve this problem. It's important. This is very important, right? Because if we want to add types to Elixir, we cannot ignore all the Elixir code that we have today, right? But all those options, they look confusing in one way or the other. So we were thinking about this, Beppe, Guillaume, and we were thinking about this problem, what we want to do. And one of the things that I have always said is that Elixir code is assertive because we have patterns and because we have guards, okay? In practice, if our identity function is expected to receive an integer, what we would most likely write is this. We would have a guard that actually checks that the argument is an integer. So here's an idea. In Elixir, patterns and guards lead to assertive code. We usually know the types that we are working on, that we are working with, okay? In fact, this is the dialyzer wisdom. This is what dialyzer used to find bugs. When dialyzer finds a bug in the code, it's because it's looking at the patterns, it's looking at the guards in your code, getting information from that, and trying to find bugs. So that's what I told Beppe and Guillaume, and then they started thinking. They're like, can we somehow leverage the runtime checks in the Erlang virtual machine? Because the third solution looked nice, right? It solved the problems, but it introduced performance costs. But if the Erlang virtual machine is already checking all those things for us, right, can we somehow leverage this? So as part of the research, we developed a whole new technique for gradual typing, which we call strong arrows. And I'm going to explain the overall idea. I want to build intuition with you. Again, as I said, my whole plan here is to build intuition so you can understand why our type system is different than something like TypeScript. But if at the end of the day you just want to use it, right, you'll be able to purge this talk from your head, okay? So what is the idea with strong arrows? If we look at this code here, okay, if we look at the identity function that we modify with a guard, we can look at this and say, if you give anything that is not an integer to this function, what is going to happen? It's going to crash. Right? So if I give anything that is not an integer, this function is going to crash. Let's take this other example, the slightly modified debug function. Right? This function, the binary, the string concatenator operator in Elixir, it expects both arguments to be binary. So we can look at this function and we know if I give anything else that is not a binary, okay, it's going to crash, right? That's the assertive code. We are checking the types all the time, right? This function here, increment, right? We have a number increment by 1. If it receives an integer, returns an integer. If it receives a float, returns a float. If we give anything else, it's going to crash because the plus operator only works with integers and floats, right? So what I'm saying is that a lot of the code that we write, it's already going to crash if we give something that is not part of the input. But we are looking at the code in here, right? And we are able to look at the code, understand, and arrive to this consequence, to this conclusion, sorry. So the idea is, can we do this somehow automatically? Can we somehow say, look, if this function, if I give something that is not part of the input, and it crashes, can we somehow detect this automatically? And because of set periodic types, we can. Here's the idea. If a function goes from A to B, so it receives an argument that I'm calling A, and returns something that I'm calling B. If we negate the domain, so domain means the inputs. It's a fancy word for inputs. If we negate the domain, if we negate the inputs, and because we're talking about set theory, I can do the negation of a set. The negation of if I say that something is not an integer, what does it mean? It means that it's everything else. It means that it's going to be a float, or a map, or a tuple. It's not an integer, right? So I can negate set. So if we negate the domain, and we type check, and there's an asterisk here because it's a slightly modified type checking algorithm, implementation detail. If it errors, then it is a strong arrow. So the idea here is that we're going to get the identity function, and we are going to type check it with not integer. If it errors, which is going to be the case, right? If the type checking fails, we're going to say this is a strong arrow, right? The same thing, we get the type here binary, we negate it, and then we're like, look, if this thing fails to type check, which is going to be the case because the string concatenation operator is not going to like anything that is not a binary, right? It fails type check, so that's a strong arrow. The same thing here, we check if we give not an integer float, if it fails to type check, that's a strong arrow. And the ideal strong arrow is that we are proving that if we call it with something outside of the domain, outside of the input, it's going to crash. So if you call a strong arrow with dynamic types, it's guaranteed that it will return its type, right? This means we can do the option tree that we're talking about without introducing additional runtime checks, okay? And that's the insight. We are using what the Erlang virtual machine does, all the type checking that happens at runtime, to prove like, hey, this code is going to fail if you give a dynamic. So that's an example, right? So no additional runtime checks required. Otherwise, we must fall back to the two options 1, 2, and 3. So let's go look at this example, right? If we use the guard, what is going to happen? This is a strong arrow, right? The identity function here, it's a strong arrow because if we give anything that is not an integer to it, it's going to crash. Because it is a strong arrow, when we call identity with dynamic, we're going to say, hey, it's going to return an integer. So the type checker is going to fail. And when we call it at runtime, it's going to fail as well. It's the consistent behavior that we want, right? So this is a new insight. There is nobody which is doing this in any other programming language because it's something that is being designed like specifically for Elixir in the Erlang virtual machine. And there is something that is really cool is that strong arrows are transitive. So let's look at this code again. We have the subtract function, all right? It receives integer, returns an integer, is implemented at A plus negate B, right? And then we have the negate function here that receives an integer and negates the integer. We know that negate is a strong arrow, right? Because we are checking the types. If we can look at it and say, if I give it anything that is not an integer, this function is going to crash, therefore it's a strong arrow. Because negate is a strong arrow, subtract is also going to be a strong arrow, right? Even without the guards. And this is very important. Remember that I said that the dynamic type, it spreads through the system, and then as it spreads through the system, the type system can prove fewer things, and therefore is not as useful. With the strong arrows, right, we have a property that is also transitive, that it also spreads out to eliminate the use of dynamic, okay? So I'm going to sum up what all this means really soon. What are the benefits that we're going to get from this, okay? There's just something else I need to talk about, which is type inference. I said that, hey, if you have the Elixir code today, we can assume that what it does is that if you don't declare the types for this, that it receives that all arguments are dynamic, right? So A has a dynamic type, B has a dynamic type. So some programming languages, what they do is that if you don't declare the types, they try to automatically infer the type based on the code. This is a property that we call type inference. So what we do is that if you don't put the types for your code, it looks at the code and tries to figure out the types. Unfortunately, type inference for set theoretic types is still a research topic, and it's very expensive. That's generally the case. The more expressive the type system is, the harder, more expensive type inference is. So this is a downside, okay? This is a downside of set theoretic types. We don't get type inference, right? However, we developed rules to infer the types of patterns and guards for set theoretic types. So if you write this code, which obviously has a bug, you say, look, int is an integer, and then you try to do the string concatenation, we are going to infer from the guards, from the patterns, right, that int is an integer, and we are going to raise an error. And this is dynamic code. This is an Elixir code today. So what I'm saying is that even when we add static types, right, and you say, look, Elixir now is statically typed, even your dynamic code, if there are obvious errors, we'll be able to find those and give you feedback. That's what all this means. So type inference from patterns and guards. We want to look at the patterns, we want to look at the guards, and we want to infer the types. So it relies on existing best practices today, because that's what we are doing. We are using patterns, we are using guards. Existing code may benefit from static typing without adding any annotation, and that's what all this means. The whole idea with strong arrows, the whole idea is saying, look, we have strong arrows, therefore we don't have to be sending dynamic everywhere, or we are going to infer the types from patterns and guards. The whole point is that when we start adding the type system, you don't have to necessarily change any of the Elixir code you wrote so far, and we'll do our best to find bugs that are proven to be bugs in the code that you already wrote today. Okay? That's what we're trying to do here. And dual type inference based on patterns and guards is nice because the Erlang virtual machine also uses the patterns, also uses the guards for code optimization. So that's why it's an important practice, and that's why it's important for us to use it, because the Erlang virtual machine uses to optimize your code. We are going to use it to find bugs. So if we put everything together, if we are talking about gradual set theoretic types, okay, we talked how set theoretic types, they express many of Elixir idioms with precision. They capture the intent of Elixir code. They provide a simple foundation for reasoning, because all we have been doing is talking about unions, intersections, negations. And the idea of gradual typing is that it allows the interaction between static and dynamic code. So all the code that we have today, which is dynamic, will be able to interact with any future code that is static. That's the gradual typing. But as we talked about, like, gradual typing relies on the dynamic type. All of our code today has this dynamic type. And when we have the dynamic type, there is not much we can prove. We cannot get many helpful compilation warnings. So our type system has two features to tame the dynamic type, to make sure that we don't have a lot of dynamic happening in our code. And those two features are strong arrows, which allows us to remove the dynamic type without additional runtime checks, and type inference based on patterns and guards. So this is the foundation of the Elixir type system, right? Those are the most important trade-offs, most important decisions that we've made so far, right? If Sasha Juric was here, he would say, like, this is the soul of the Elixir type system. And this is very exciting because there is nobody doing this, right? This is something new. This is something specific for Elixir. We are really trying to capture the intent of our code. We are really trying to capture the code that we already wrote today and give you warnings, giving you benefits, okay? But at the same time, it's quite scary, right? Because there's nobody doing this, right? So there's a chance that we struck code and found something really nice that really fits Elixir. But because it's new, it's something specific to us, we can only draw limited comparisons to other type systems, right? So if somebody says, hey, I use TypeScript, and TypeScript is gradually typed, and I did not have a good time. Therefore, I won't like the Elixir type system. Well, that's not necessarily the case. We are making different decisions. Not only that, right? Elixir is functional, immutable, right? TypeScript is object-oriented, mutable. So there are many differences, right? But that's what we have been working on, okay? This is the digest of what I've learned in the last 18 months. All right, so we are going 1 hour in. We are going to the end of the talk. And one of the things that I want to do is to do a preemptive Q&A, all right? So I want to address, like, as I said, there were questions on Twitter, there were questions on the Elixir forum, and some of those are very common. And now that we understand the foundations, why we have made those choices, we can answer those questions with an understanding of why. So for example, will the new type system support spec, right? No, we don't plan to integrate with spec. And why is that? Because the specs that we wrote today, we were most likely not thinking about type precision. It's most likely they're not as precise as they should be. So I want us, when we add the types, for us to really think about the best way to write those new types. Okay, so it's not going to integrate with spec. The plan is that if everything works out, we are going to move spec to a package, to a dependency for those who really need it, but it's not really going to be a part of Elixir anymore. Will the type system be enforced on me, right? So if for some reason you don't want to write the types, right? You don't have to. It's a gradual type system. But not only that, if you say, hey, I don't want to write the types, as I showed, we are going to do our best that even if we don't write the types, even if you don't write the types, we are going to look at your code, and we are going to try to find possible type violations, type checking bugs in your code, even if you don't write any type at all, because we have this idea of strong arrows. We have this type inference from patterns and guards. Okay? Will the type system return mismatched types at runtime versus compile time? It's going to be unsound like TypeScript. Like, that's a very common question. We talked about this. Like, the whole idea of strong arrows is that we don't have to do that. We don't have to say, hey, this thing returns an integer, but when we look at it at runtime, it's a string. And we can do that without introducing additional runtime type checks. Right? So, no, we are not going to do this. We are taking a different approach. Will the type system work with macros? So what is a macro? A macro is a function that is called at compilation time that receives AST and returns AST. So this means that for all macros, we already know what are the inputs and the outputs, right? So the type system will work just fine with macros, and maybe even better, we can automatically start type checking them because we already know what is the type signature of all inputs and all outputs. Will the type system work with existing tooling, such as IDEs? Yes, and potentially yes. So the Elixir compiler already has the whole infrastructure, so like the language server and IDEs, they hook into the Elixir compiler, which emits warnings and everything. And when we integrate the type system, it's just going to use the same infrastructure. So when the type system emits a warning, it's going to automatically appear in your editor. But your IDE most likely can have other features, like, oh, I'm going to press this key, and it's going to show the types of all variables. For those additional features, then yeah, the Elixir team will have to work on new APIs. The IDE developers or language server developers, they'll have to integrate with those APIs. That's work we'll have to do. Will the type system be backwards incompatible, break the language? No, it's gradual, right? We are being very intentional about this. We don't want to break our code. And not only we don't want to break our code, we want to make sure that we can find bugs in your code, even if you don't write the types. Will the type system make Elixir harder to learn? That's a very good question, right? And honestly, I don't know the answer. I can see indication that, oh, it may make easier, because if we can have, our focus is going to be on having good error messages. And if we can show you errors early on as you're writing the code, then that can be really positive for the developer experience and the learning experience. But at the same time, even though it's a set theoretic type system and we can reason about it, thinking about unions, intersections, negation, right? the type system, we want to make it easy to reason about. So even though it's easy to reason about, it doesn't change the fact that, yeah, it's going to be something new that we'll have to learn, right? It's going to be part of our journey. So the idea is that, well, maybe even if it's going to make the learning curve maybe a bit longer, it's going to smoothen parts of it. And hopefully, it's not going to make Elixir harder to learn, but there is no answer. We'll have to work for this. And it's something that we have to keep in our mind. Will the type system work with message passing, processes, Phoenix pub sub? Yes and no, right? Because all we're going to do is say, hey, you receive a message, it's dynamic, right? It's an easy cop-out. We just say it's dynamic. And we can use the strong arrows, we can use the pattern matching and guards to prune that dynamic, but we just say it's dynamic. It's something that we only know what it is at runtime. Will the type system slow down the compiler? That's, who thinks this, who is worried about this? Who is worried about compilation times? Nice, not many, yeah. Elixir 1.15 did huge improvements to compilation time, but this, to me, it's one of the biggest concerns. Because, and as we head towards development, this could be something that, oh, we added the types, but Elixir compiles 3 times, 4 times slower. Then honestly, I'm not sure if it's going to be worth it. So this, when we say, look, we may still not have a type system at the end, it's because this can be a potential reason. So this is a big concern, and we will figure out as we develop and implement it. Last one for now, and then we can have yours. Questions. Will the type system split the ecosystem, right? And technically, no. As I said, it's a gradual type system. We're not going to fork the language. But there is no denying that if we add a type system to Elixir, it's going to potentially change some of the practices that we have today. Some code, some idioms. Maybe you say, maybe that's not the best way to write this anymore. Now we can write this in this slightly different way that is going to suit the type system better. That can be a possibility, right? So technically, it's not going to split the ecosystem, but it can be as we move forward, as we learn new patterns, learn new idioms, that we want to change a couple of approaches. And then some projects, some ideas in the community will have to move away from or explore other directions, and that can generate a split. So it's our responsibility when this happens, when we are in this period of learning and incorporating the type system, if it happens, that we deal this transition with patience, with grace. And this is not up to the Elixir team, right? It's up to all of us. It's up to the ecosystem. It's up to the community. All right, last 5 slides. Other features. So again, for those who are type curious, there are other features necessary in order to type everything that you can do in Elixir. So the paper talks about parametric polymorphism, protocols, exhaustivity checking, redundancy checking, type of structs and maps. There are many things in there. If you are type curious, if you're interested in the details, check it out. And we also have future work. So for example, some of this is already ongoing research, such as occurrence typing. And so it's a discipline that is going to allow us to provide more precise types for conditionals. Row polymorphism. So if you wanted to say, look, this function receives a map and returns a map with this key added or this key was removed, we need a whole subclass of typing to do that, which is called row polymorphism, which it's being researched. So, and then we also want to research something that we call existential types. The type system we have today that I've showed so far can type the behaviors, like Jun server and behaviors that we have in Elixir. It can type what we have today. But there is this theory called existential types that would allow us to provide really precise and strong in the sense that it will be able to validate a lot of our behavior implementations in our code, which is something that we want to research. There is no research happening on this right now. So if you are interested, if you are a postdoc student or you know someone who may be interested in research this, please let me know. We are looking for a postdoc to explore existential types within set theoretic types. Anyway, again, this is something very specific. The point is, we are done with research. Mostly, we are going to focus in development, but there is still very precise research happening in one another areas to make the type system more precise, more useful, more helpful to us. And finally, what is the roadmap, right? So I'm glad, no, I'm not announcing anything. Roadmap. Our goal is to add set theoretic types to the compiler and infer types from patterns and guards. This is what we want to, the first thing we're going to do. So the idea is that we're going to implement the set theoretic types, and we're only going to add to the compiler, and we are going to infer the types from patterns and guards, so we can show you and error messages, we can find obvious bugs without you having to change a single line of our code. And the reason why we're doing this is because it's going to allow us to improve the error messages, to make sure that the type system is fast without imposing any churn, any change in the community, okay? Then if this works out, if you are happy, the first thing that we are going to allow you to type in your Elixir code is structs. Right? Because we have patterns and guards, and that has a lot of type information, as I said several times, right? But also what we want to do, the other thing that you use a lot in your code is structs. So we want to allow you to add types to our structs, because that's going to be even more type information that can propagate through the system. And then if this works out and we are happy, then we are going to add like the whole thing, like typing functions, the signatures, and so on. As I said, there is no roadmap, there is no deadline, there is no, sorry, there is a roadmap. There is a roadmap, but there is no deadline, there is no date where like, oh, that's when we're going to have it. That's when we're going to have it. As I said, we may not have a type system at all. The only guarantee that we can, that I can give is that we are giving it like a honest try. And we are being very careful, very intentional in our decisions. So if at the end of this, regardless if we have a type system or not, we understand the whole process and we understand the conclusion that we will arrive to. Thank you very much.